Yeah, can you see my screen?
Yes, visible.
Okay, yeah, so then you can start. So, recall that yesterday we were looking at like a randomized algorithm for the problem where randomized algorithm that uh, would detect whether a bipartite graph has a perfect matching or not. And we did look at the algorithm, but we proved some things. So we saw what the bi-adjacency matrix of a bipartite graph is, and we proved that a perfect matching exists if and only if there exists a permutation such that mi sigma is 1 for all I in M, i.e., corresponding to every perfect matching, there is a permutation. Then we saw the definition of the permanent polynomial, and we saw that the number of perfect matchings in G is exactly equal to the permanent of M. And at a very high level, what was happening in the proof was that over here we saw that corresponding to every perfect matching, there is a permutation. And over here we saw that, uh, ev- okay, so the bi-adjacency matrix is going to be a 0, 1 matrix. And so this sum would just be the count of the number of permutations such that this is 1. And so there is also a 1-to-1 correspondence between, uh, yeah, 1-to-1 correspondence between, okay, so write this permanent as a sum of ones. There's a 1-to-1 correspondence between ones in this sum and the permutations for the permutations. And these permutations also correspond, have sort of a 1-to-1 correspondence with perfect matching, right? That is what was happening in this plot.
Yes.
Yeah, and so yesterday we also briefly discussed an answer to this question. Okay, so we discussed yesterday that if you want to come up with an algebraic algorithm for a problem, come up with a polynomial that captures the problem's answer polynomial, the permanent, and we saw that the number of perfect matches is exactly equal to the permanent of M. So, so the question that we looked at was why cannot we get a deterministic algorithm for for detecting whether a graph has a perfect matching or not using this permanent polynomial, right? Because all we have to do is, given the bipartite graph, compute M, its bi-adjacency matrix, which is fairly straightforward, and then compute its permanent. If it's 0, then there are no perfect matchings. If it's any number other than 0, then there is a perfect matching, right? And we saw an answer to this, and the answer is that we do not know how to compute the permanent efficiently. In fact, we believe that computing the permanent is a very hard problem, right? So we did not get a deterministic algorithm because
But then I have a question here that
yeah.
what is preventing us to, I mean, not to compute the permanent of M efficiently?
Okay, so I don't think we know an answer to that question. So that's exact. Okay, the question is equivalent to the question of why is permanent hard?
Yes.
Yeah. So and that question is essentially the question of FP versus Sharpie, right?
How, I mean, what is the link in between getting the permanent polynomial and then proving P is equal to NP kind of the thing?
Okay, so we know that permanent is Sharpie complete, right? Even
Oh,
the
yes,
0, 1 permanent is Sharpie complete.
yes. Right.
Yeah. So if you can compute permanent efficiently, then yeah, all of Sharpie is an FP, right?
Yes.
Yeah. Okay. In fact, let me say we believe. And so this does not give us a deterministic algorithm for the perfect matching problem, but we would still salvage something from this. So we would, using what we have seen so far, we would construct a polynomial that this polynomial would be zero if and only if the graph has no perfect matchings. Okay. And to construct this polynomial, uh, we'll see what we'll look at something called the Tutte matrix, and I don't think we have looked at this before. Yeah. Okay. So let me define this. Ah, is a how much fat do I have? Yeah, it should last 1.5 years. Okay, let me call it T. I am assuming that G has n vertices on both sides. Uh, yes, this is how the matrix is defined. Uh, if uh, if the Mij entry is non-zero, i.e., if the Mij entry is one and there is an edge between I and j, then the ijth entry of the matrix of the two-way matrix is xij, a variable. Otherwise, it's zero. Okay.
And what is Xij here is?
So xij is some variable.
Okay, okay.
Yeah. Okay. So this is a matrix whose entries are either zeros or variables. Okay.
Yes.
Yeah. So now that we have this matrix, let's first look at let's first look at the description of an algorithm, and then then I'll explain why it works, and we'll look at its success probability. Okay. So the algorithm does the following. Okay.
So what this symbol, special
Yeah.
symbol here is, this seems like an XOR.
Oh, okay. Okay. So the symbol is this, and it's called the disjoint union.
Okay, okay.
Yeah. So basically, the plus inside denotes that the union is disjoint.
But union is always disjoint, isn't it?
Oh, no, no. Okay. So for example, This is not a disjoint union because both of these have a common element, right? So what this denotes is that L and R are two sets which are disjoint, and I'm taking the union.
Oh, yes, yes, I understood. Yeah.
See, no otherwise. Okay, the algorithm proceeds as follows. So xi aij. So if the determinant of t prime is output, no other. It is fairly simple. You compute the two-way matrix of G, which you can easily do from the bi-adjacency matrix, and then you replace every variable xij with a random a value aij with uniformly at random from M. Well, here M is some number which you will fix later, depending on what we see in the surface. And T prime is the two-way matrix, but they are replaced by aij. And we compute the determinant of T prime. If it's zero, we output that no, the graph does not have a perfect matching. And if it's non-zero, we say that the
So why is this so? I mean, is this algorithm complete? Because we are replacing wherever we find the values as one in the bi-adjacency matrix. So we are replacing those ones by the
yes,
variable say xij, and then we are
right.
replacing this xij by some value and which has been picked randomly. So if
Right.
I replace all those xij's by some randomly picked value, then what does it mean that if
Hmm.
the determinant of the t prime is not equals to zero, then yeah.
Okay, so
So
modulo the Schwarzschild lemma, this just means that the polynomial determinant of T is non-zero, right?
yes,
Yeah. So there is some small probability of failure, but apart from if you ignore that, then this just is that this polynomial is not identically zero, right?
yes. Oh, I see,
The
I see.
claim
So
that
basically,
yeah.
okay. So the determinant of the matrix T prime is basically a polynomial.
Okay, no, determinant of T prime is a number, determinant of T is a polynomial because the entries of T are variables or zeros, right?
I could not understand this. That why so? I can
Okay,
understand the
so what
determinant
are
of the matrix T would be a polynomial, but I mean, what is the relation in between the determinant of T and the determinant of T prime?
okay, so the determinant of T prime is just the evaluation of the polynomial determinant of T at a random point.
Yes, yes.
Lemma. This mean this means that whenever the determinant of T prime is non-zero, if and only if the polynomial determinant of T is zero, modulo the error that you get from the Schwarzschild, right?
Actually, your video got freezed for some time, so I could only hear till this
Okay.
point that you took the help of some lemma. I mean that it is difficult for
Yeah,
me to
the
pronounce the
Schwarzschild
name of
lemma.
it. Yes, yes, yes. But then
Yeah.
that lemma
So,
used to say that the polynomial is equal to 0 with the probability of less than or equals to, say, d by the modulo of s.
right. Yeah. So
So,
there
so
is
what is
there is
here
this
and
error
what is the
probability.
modulo of s here?
Oh, so S is M over here, right?
Okay, okay.
Yeah. And we will fix the size of M, or we'll fix the value of M in the analysis.
Ah, okay, okay.
Yeah. Okay, so now let's just quickly look at the running time. So computing the 2T matrix takes order n square time at most, because there are only n many ij's, sorry, n square many ij's. Yeah, then like picking random values also takes order n square time, and computing the determinant of an n cross n matrix takes order n cube time, right? So the running time is order n cube. So is this
But
fine?
computing the determinant takes the linear amount of the time. Yesterday we
So,
saw this.
okay, it doesn't take linear time, right? It takes polynomial time. Okay,
Okay.
so how would you compute the determinant?
So
By
I'll
Gaussian
pick the
elimination, right?
first row by ignoring the first row and the first column and then computing the, I mean, the determinant of that
Oh,
thing.
so
So that
if you do it like that, then the running time would be something like this, right? Tn is equal to n times Tn minus 1 plus order n, right?
yes.
But this is bad, right? Because this is n square Tn minus 2 plus something. And if you do this, you get, oh, sorry, this is n, yeah, not this, it's n times n minus 1 Tn minus 2 plus something, right? So if you do it like this,
Yes.
you get n times n minus 1 all the way to 1, which is n factorial.
Factorial. Oh, I see.
Yeah, so this is terrible, right? So the way you can do this is the following. So we saw that if the matrix were upper triangular, then the determinant would just be the product of the diagonal entries, right?
Yes, yes.
So you just try to make the matrix upper triangular, and how can you do that? So take the first row. Uh, okay, yeah, take the first row and basically try to make every entry of the first column except the one in the first row zero, right?
Hmm. Hmm.
By basically using row operations.
Yes, yes, yes.
Yeah, so now all the entries in the first column are zero except the first one. Then make all the entries in the second column except the first two entries zero, and so on, right?
Hmm.
Now, if I wanted to make all the entries in the first column zero, I have to subtract the first column, first row from the second row, from the third row, and so on,
Hmm.
right? So there are n minus one row operations, and each row operation itself costs me order n, right? Because there are n elements in the row.
Hmm. Yes, yes.
So yeah, for every column, it costs me or roughly order n square, and there are n many columns. So it's like
Oh,
roughly order n cube.
yes, yes, yes.
Yeah. Yeah. So the running time is order n cube. So now let's look at the success probability. So for that, okay, there are always two cases. G has perfect matching and G does not have a perfect matching. But before going into those two cases, we would first prove a claim which you would use in both of them. The permanent of the biadjacency matrix is equal to the number of perfect matching, right? Today, what we'll see is that the determinant of the 2T matrix is a zero polynomial if and only if G has no perfect match. Okay, so is
Okay.
this fine?
Yes.
Is the claim fine?
Yes, so if the polynomial comes out to be 0, then G has no perfect
Right.
match. Yeah,
Yes. Okay.
because yeah,
Yeah,
if
so
the yeah, yeah, true, right.
okay, so I don't have enough space. Ah, okay. Okay. So, like, like before I show you the proof, let me just, okay, so we saw two ways to compute the determinant, right? One using the hide the first row, hide the first column, everything. So one using minors of the matrix, another using Gaussian elimination. Turns out there is a third definition of determinant, and it's this. So it's very similar to the definition for the permanent. Yes, with this is you can show that this definition of the determinant and the definition using minors or using Gaussian elimination are equivalent. Okay. The only difference from the permanent is this time term. So is this
Yes.
definition fine? Yeah.
Yes. Yes. Yeah.
Okay. So now that we have this definition, we can sort of see what would happen, right? Again, we would work with permutations. So let me prove this direction. So yeah, if the determinant of t is non isn't okay, if the determinant of t is okay, I should have written the claim like this. Yeah, this is nicer. So okay, I've changed the claim. The claim is now the determinant of t is non-zero if and only if G has a perfect matching. The two claims are equivalent, right? The determinant of t is zero if and only if G has no perfect matching, and determinant of t is non-zero if and only if G has a perfect matching.
Right. Because then we would be having some entries as one. I mean some
So
t entries as one.
some entries at xij's.
Some entries as
Xij's because we are looking at the two-way matrix, right?
yes. 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 Some
Yeah.
entries as xij.
So
Right. Right.
yeah, in the bi-adjacency matrix, those would be one. Here they would be xij's.
Yes. Yes.
Right. So the determinant of t is non-zero. What does that mean? That means that at least one of these products is non-zero, right?
Yes.
Yeah. Which means that there exists which implies that okay, so we have that product I in n, xi sigma is non-zero. But whenever you have xi sigma I in the two-way matrix, what do you have in the adjacency matrix? You have this, right?
Mi comma sigma n.
Yes,
Mi comma sigma. Yes.
right. Which implies for all I and n, this is one, right? Which in turn implies that this set is a subset of P, but this set matching, right? Yeah, so the set I comma sigma I goes in n, I in n is a perfect matching, right?
Yes. Yes.
Yeah, so if the determinant of the two Yeah.
So
For the sake,
you,
yeah.
I mean, you became mute actually, so I could not hear you.
Oh, okay.
I could hear you till this
Oh, so
point that, but this is a perfect matching, and after that,
oh yeah. So this is a perfect matching. So I said that if so, we have shown that if the determinant is a non-zero polynomial, then a perfect matching exists, right?
yes, yes, yes,
Yeah. Okay, so now we need to show the sort of the reverse direction. If a perfect matching exists, then the determinant is non-zero.
yes,
Okay, so a perfect matching exists. So let's say, mm, yeah. So if I comma gi is the perfect matching, then J1 to Jn must be distinct,
yes,
and uh, this set must be equal to n, right? So the mapping I to Ji is 1, 1 and on 2. So sigma I defined as Ji is a permutation, right? Is this fine?
yes, yes,
Yeah. So now that it's a permutation, so why? Because all of these edges exist in the graph. So this implies that Ti sigma I Ti sigma I is equal to Xi sigma I for all I in M. Right. Thus, determinant of T contains the monomial product I in N. Yeah, so the determinant contains this at least this one monomial in it. And so it's a polynomial that contains one monomial. The coefficient of that monomial is 1. So the polynomial is non-zero, right?
yes, yes, yes,
Yeah. Okay, so now we have what we wanted, right? We have a polynomial which you can evaluate efficiently, and the polynomial is 0 if and only if there are no perfect matches, right?
yes,
So now we can just use Schwarzschild, which is exactly what the algorithm does, right? Yeah, it just evaluates the determinant of t at a random point. Okay, so again, let's analyze the first case when G has no perfect matching. So in this case, what would the algorithm out?
yes. So algorithm will not give any output. It will not generate any output.
So it always generates an output, right?
But then, so
And
it outputs no matching. What is it in here? No.
yeah,
I
okay,
mean,
it outputs no otherwise.
okay, okay, yes,
Yeah, yeah. So it outputs no, right? With
yes,
probability 1, because if there is no perfect matching, then the determinant of the 2K matrix is 0. Sorry,
y-
yeah, that polynomial is identically 0. So no matter
yes,
at which point I evaluate it, the output, the evaluation would still be 0, right?
yes,
Yeah, so in this case, no. Okay, so now the second case is interesting. So G has a perfect matching. So in this case, we know that from claim 3, this polynomial is not now determinant of T prime is just the determinant of T evaluated at a evaluated at this point, right? And a determinant of T has this relationship.
So I could not understand this point here that determinant of t prime is equal to the determinant of t and then multiplied by, I mean, why this aij we are writing again? I mean,
So this is a polynomial. What I'm saying is this polynomial is evaluated at this point.
okay, okay.
Yeah.
Mhm.
Okay, so let me bring this closer so it would look like an evaluation. Yeah. Okay, and we know that AIJs are random, right? So we can use Schwarzschild, but we need to do one more thing to use Schwarzschild. So what is that one thing?
So yeah, I need to somehow, I mean, determine that d part, that what would be the degree of the polynomial we are dealing with.
Exactly, yes. So we need the degree of determinant of T, right?
Yes.
Okay, but this is what the determinant of T looks like, right? And
Yes.
these things would be replaced by xi sigma r.
Yes.
So the degree of the determinant would be the maximum of degree of these monomials, right?
Yes. 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 So
And
that would be
what's the degree of
n
every
nx.
monomial? Yeah. What's the degree of every monomial? You said something, right?
Yeah, I said that degree of every, I mean, in this case would be equals to, because I is getting mapped to its permutation. So
Right.
therefore, the degree of everything would be equals to 2,
Oh, no,
and
it
then
would be n.
things
It
are
would be
getting
n, right?
multiplied.
Because, okay, so this is a monomial, right?
Yes, yes.
And this
Okay.
is a variable. How many
Okay.
variables are being multiplied? N many variables are being multiplied, right?
Yes, 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 yes.
Yeah. So the degree is n.
Right.
Now we can use Schwarzschild, right? So this is at most the degree over m, right? So this is at most half. And we again know how to boost this probability, right?
Yes, yes, yes.
Okay, so question, what type of algorithm is this?
One-sided Monte Carlo.
Yes. Yeah, so in fact, almost anything that depends on Schwarzschild lemma would end up being something like this, because the Schwarzschild lemma itself gives you a very natural algorithm, which is one-sided error Monte Carlo, right?
Yes, yes.
Yeah. Okay, so is this fine?
Yes, yes, it is fine.
So then, okay, so here's one question which you would solve in the problem solving session. So give a deterministic algorithm to decide if the number of perfect matchings in a bipartite graph is odd or even. Now I'm not interested in knowing whether there is a perfect matching or not. I'm not even interested in the exact number of perfect matchings. What I'm interested in is whether the number is zero, whether the number is odd or even. Okay. So for example, if there is one perfect matching in the graph, I wanted to say that I want the algorithm to output odd. And if there are two perfect matchings or zero perfect matchings or four perfect matchings, I want the algorithm to output even, right? So this is the problem. So is the problem fine?
So yeah, yeah. So can you mark this problem? I mean, can you use some remark here just to note just for me to remember that you would be solving this problem in the last session?
Okay. So anything with question and anything with QUE and underline, I would solve in the problem solving session throughout the notes.
Yes, yes. All right, all right. Yeah.
Yeah, so I think I've also been doing this for other things. Let me check. Yes, this was something we discussed yesterday, right?
Yes, yes. Yeah.
Yeah. Okay, so I wanted to show you a randomized algorithm for one more problem, checking if two sets are the same or things. Let let's first look at something something more for perfect matchings, and then if we have then next week we'll come back to this problem of checking if two sets are the same or not. Because yeah, let's just maintain continuity. Okay, so okay, so right now we just saw a randomized algorithm for determining whether a graph has a perfect matching or not, right?
Yes,
But that
yes.
algorithm does not find a perfect matching, right?
Yes.
Yeah. So what we'll see now is a randomized algorithm, in fact, a randomized parallel algorithm for finding perfect matching in bipartite graphs. And yeah, so I want to cover it now because this has some similarities with it. The approach is exactly the same. It's find okay, take a take the determinant of of the 2K matrix, evaluate it. It's something like that. So yeah, let's just cover this now. Yeah. So this is actually the content I had planned for today, but yeah, as usual, we are little like yeah, we are a little late. So yeah, so far we saw randomized algorithm for checking if two matrices are similar and if a bipartite graph is a perfect matching or not. We haven't seen this. We'll see this next week. And now we'll look at two things. First is an isolation. First is the isolation lemma, and then we'll look at the MVV algorithm to find perfect matches in bipartite graphs. So what I'll do today is I'll just give you the statement of the isolation lemma. I won't prove it. We'll see. We'll look at a proof next week. But today we'll use that lemma to give this algorithm. Okay.
Yes, yes.
In lecture 9, we can look at isolation lemma and this algorithm for checking if two sets are the same or not. Yeah.
Yes, yes. Okay. So okay, give me a minute. I could not hear you. What did you say? In case you are speaking something, you are not audible.
Oh, okay. I'm not saying anything. I just got up to get something. Yeah. Uh, okay. Yeah. So before we look, okay. So now you can hear me, right?
Yes, yes, I can hear you now.
Okay. So before we look at yes. Oh, let me move that. So before we look at the isolation lemma, so the isolation lemma is what a set system is. So a set system contains two components, a family of subsets of the universe. So set system is a tuple u comma f, where u is a finite set. Let's say it's x1. Let's say it's x1 to xn, and so over here u is called the universe, and script f or f is a collection of sets s1 to sm. Oh, this should be si, not si. Yeah. So the family F is a collection of subsets S1 to Sm of this of U. Okay. So is the definition of a set system clear?
No, it is not that clear actually. I could only understand this thing that I mean this topology is set system, and wherein the cardinality of the first set is equal to n, and then we are so what these x1 to xn are these are the I mean are these elements of the set U or what? But then the weights are assigned to these variables. So I could not completely comprehend this thing. Yeah, what the set
Okay,
system
so
is.
X1
Uh, Actually, your
is
video
any.
got fixed, so this is the thing.
Okay, okay,
Yeah.
okay. So I okay. So I was saying that X1 to Xn are elements of U, and they can be anything. They can be variables. They can be numbers. Yeah, they can be pretty much anything.
Okay. Okay.
Yeah. And the collection F is a set of subsets of U. So for example, S1 can look like X1, X3, X4. S2 can look like X1 to Xn minus 1 and so on. Okay,
Okay. Okay. And there would be 2 raised to the power n possible subsets. Is this valid?
right. Yes, but out of them, only some of them
Only some of them
are in this family F.
okay. Okay. Okay.
Yeah.
And why are we assigning weights to, I mean, these variables, say x1 to xn?
Oh, in the isolation lemma.
Uh,
So okay, in the definition of a set system, there are no weights. The weights are only assigned in the isolation lemma.
okay. Okay.
Yeah. Yeah. So is the definition fine? So a set system is a collection of is a two tuple. The first element of the tuple is a set. The second element is a is a collection of subsets of the first element, right?
Yes. Yes.
Yeah. Okay. And now the isolation lemma says that if U comma F is a set system where size of U is n, then what we'll do is we'll assign weights Wx1 to Wxn with the elements x1 to xn of U and define a weight function, which is a which U. So this notation
Again, I could not hear you, but
okay. So I was saying that this notation 2 to the U denotes the power set of U.
okay. Okay.
Can you hear me?
Yes. So I could hear till this point that 2 raised to the power u is the power set of u. I understood.
Yeah. So okay. Yeah. So the weight function is from 2 to the U to Z. So the weight function assigns weight to every subset of U, right?
Okay. Okay. Yes.
Yeah. Yeah, and how do I define the weight function? So for any subset S of U, weight function of S is equal to the sum over all x in S of Wx. So it's just the sum of the individual weights of all elements of the set, right?
Yes, yes, yes.
Yeah. So for example, if S were x1, x2, x3, then its weight would be W1 plus W2 plus W3. Okay.
Yes, yes.
Yeah.
And what this
Sure.
WC here stands for?
This
I
one.
mean, this one, yeah.
Oh, okay. This is W subset of Z. Okay. Let me write this in the lexicon.
Okay, okay.
Yeah. Yeah. Then for any W's, which is a subset of Z, it should be W. Yeah. Then if I were to pick the weights of x1 to xn uniformly at random from the set W, and the probability that there exists a unique set F. Okay, I've been using S for set, so let me use S over here as well. Then the probability that there exists a unique S in F, that weight of S is minimum, is at least 1 minus n over size of W.
Okay. So, I mean, what does it imply? I mean, what is the intuition behind this? What is the meaning of this thing?
All it is saying is, okay, so I am picking the weights W1, Wx, fix these weights. Uh, the weight of S for every S in the family would be fixed, right?
Yeah, yes. Actually, again, there was some disturbance
Okay.
first. Yeah.
Okay.
So,
So yeah, so that was a notification in my laptop. So okay, I can go with this again. So like I am picking W1 X1 to W1 Xn uniformly at random from W. But once I fix this, the weight function for every S is fixed, right?
yes, 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 yes.
Yeah. So now let's look at okay, let's say F is S1 to Sn. So now let me look at W, the weight function of S1 to weight function of Sn, right? Now these are just numbers.
Yes.
And what the statement is saying is the following. Let's say the minimum of these numbers is lambda. Okay,
Minimum of these numbers is
lambda.
okay.
Then what this claim is saying is that there exists just one set, so that weight of weight is, so there is only one set whose weight is minimum among all the sets.
Yes, yes, yes.
Yeah. So for example, this is saying that okay, the probability that the weight of S1 and weight of S2 is both minimum is small.
Oh, I see. So
Yeah.
I mean, so probability of having a unique minimum is greater than this quantity.
Yes, the probability of having a unique minimum value is greater than this quantity.
Okay, yes. And what this n here is, n is the number of the elements in the set U, and then
Yes,
and the mod of the W is what? So this mod of the
size of
W is
W.
size of.
W is a set, like, so W between these symbols, that means the size of W, right?
No, I could not hear this. So what this W
Oh,
here
so
is
W is a subset of Z.
Yes, that is true. But then what is the mod of the W then?
Oh, so what's mod of a set? It's the size of it, right?
Yes, so but then W here is not the set. I mean, this is a set of the weights, but then I mean, which set are we referring to?
Okay, so W is any subset of Z, right?
Okay, yes,
Because
yes.
W is any subset of Z. So let's say W is 1. Okay.
Oh,
Then what am
yes.
I doing is each of the Wx1 to Wxn is a random element in 1 to 10n, but this number is 10n. Ah, this number is 10n. Right?
Yes. So does this mean that the probability of having two minimum values, I mean two subsets having the same weight is n by w?
Okay, no. So this does not say that. All this says is that two subsets having the same weight is at most n over w if their weights are minimum. So let's say the weights are 1, 2, 3, and 4. So let's say you have m elements, but all of these elements have just 4 weights: 1, 2, 3, and 4. Okay.
Mhm.
What this statement is saying is that there is just one set with weight 1, but there can be multiple sets with weight 2, weight 3, weight 4, and so on.
Okay.
Yeah, so only the set set with the minimum weight is as a unique weight. Set with larger weights, sorry, yeah, sets whose weight function is larger need not be unique.
Yes.
So, for example, it's possible let's say you have S1, S2, S3. It's possible that their weights are 1, 2, 2. This can happen with probability 1 minus n over size of W.
Yes.
But this case, S1, S2, and S3, 1, 1, 2, this would happen only with probability n over W.
Right, but then two is having a unique. I mean, two is a unique minimum here. So again, I mean
Okay, where is,
lemma
oh, okay,
whole.
2 is not the unique minimum, right? The unique minimum, okay, the minimum over here is 1.
Yes, yes, yes. Now I understood.
Yeah,
Yeah.
yeah. So is this fine?
Yes. Yes, yes, yes.
Yeah, okay. Okay, now, so first of all, this is sort of counterintuitive because, so how many elements does F have? It has M elements, right?
Yes.
But over here, M appears nowhere. So no matter how many elements I have in F, the probability still remains the same. If I have 2 elements, the probability remains the same. If I have a million elements, the probability still remains the same.
Yes, yes, yes.
All it depends on is how many elements do I have in the universe.
Right, right.
So this is sort of counterintuitive. But we'll see a proof of this next week. They will use this to give an algorithm for finding perfect matchings in a graph, in a bipolar graph. Okay.
Yes.
Yeah. So before that, let's give us okay. So this algorithm is known as the MBB algorithm or the Mulmule-Vazirani algorithm after the people who proposed this.
Okay, okay. So Vadirani, that I mean those Umesh Vadirani and Vijay Vadirani, two brothers.
Yeah.
Is this?
Yes.
Okay.
Yeah. Okay. So before we look at the full MBB algorithm, you can even divide the MBB algorithm in two parts. The first part would detect whether the bipolar graph has a perfect matching or not. And the second part actually finds the perfect matching. Okay. So
Yes.
what I want to do is instead of giving the entire algorithm and analyzing it in one shot, let's first analyze the first part, which is an alternative algorithm for the decision version of the problem. So we already saw an algorithm for the decision version, right? Just take the two-tail matrix, evaluate its determinant at a random point and done, right?
Yes, yes, yes.
Yeah, so this is an alternative algorithm for to do the same thing. So we would first look at this, analyze the success probability, and then we would look at the algorithm for the search version. Okay.
So I have a query here at this point.
Yeah,
So yeah, yesterday you told the recipe to, apply this algebraic thing. That
right.
in your notes. That you told the protocol. The more or
Oh, okay,
less.
yeah. Oh, so you are saying
Uh,
that I should add this in my notes?
yes. So if you include that recipe tentatively, tentative recipe in your notes,
Yeah.
so that would be easier for me to understand. Yeah.
Okay, yeah. So I can, okay, let me add a page over here. I'll add it over here. Where is it? Oh, yeah. Yes, we'll add it over here.
Yeah. Thanks.
Yeah. Size of R are going to be. And so this part of the algorithm, the first part, outputs yes if the graph has a perfect matching and outputs no otherwise. Okay. So just as the previous algorithm. And okay, so the algorithm is as follows. For all E in the edge set, let me define XE to be the corresponding entry in the two-way matrix. Okay. So two-way matrix would look like its entries would be either zeros or X's.
Right.
Yeah. So now what we'll do is we'll pick WE uniformly at random from the set 2N and compute the determinant. So earlier we were replacing XE by WE and computing the determinant of the resulting matrix, right? Now what we'll do is something different. We will compute the determinant of the matrix M obtained from the two-way matrix by substituting XE with 2 to the WE.
Oh, I see. Okay.
Yeah. And again, if the determinant is non-zero, the output yes, otherwise the output no.
Then what is the reason behind, making the things complicated that, so last time we simply replaced the value of xi by
Right.
aij, and we took those values from randomly from the set M, and the things were
Yes.
a lot easier. And this time we are, replacing it by 2 raised to the power something. And why so? Your video got freezed. Video and audio. Yeah.
Yeah, so I was saying that over here, it does not make any sense. However, so when we analyze the success probability, we would observe that when you replace XE by 2 to the WE, not only is the determinant non-zero, the determinant has a very nice, that number has a very nice property. And we would use that property to find perfect matches.
Okay.
Yeah, so over here, yeah, if you just wanted to detect whether the graph is a perfect matching or not, don't do this. Just use the previous algorithm. That's much simpler.
Okay.
Yeah. Okay. So again, like we have seen running times of algorithms like this a lot, so I won't write it down, but the running time is basically, yeah, so this takes order n square time. Uh, this takes order n time. Again, you want to compute the determinant of m, but before that, you would have to compute 2 to the WE. So this you can do in time WE, right? Or even log WE.
Uh, okay. So,
Oh,
each
sorry.
each
Yeah,
value.
this you can do. So this you can do in time W. One way to do it is like just multiply 2 itself WE times. Another thing is compute 2, then 2 square, then 2, sorry, 2 to the 4 and so on.
in case if you are writing something on the slide, then that writing is not visible.
Oh, okay. Oh, so let me try to reconnect. Why can't I leave the meeting in my room? Can you see my screen?
Yes, yes, the screen is visible. Yes, and what and
Yes.
just now you write something and that was also visible.
Oh,
It
okay,
is
okay,
visible.
okay. Yeah, yeah. Yeah, so what I was saying is you can compute 2 to the WE in time WE. One way to do it is multiply 2 with itself WE times. Another would be to compute 2, then multiply 2 with itself to compute 2 square, multiply 2 square with itself to compute 2 to the 4, and so on. Yeah, so computing
Yes, but
this is not an issue. It takes order n time.
so if there are, I assume that 2 raised to the power something is not difficult to compute. The thing
Right.
is that so since we have so XE, so at the most there would be how many entries would be there in the form of XE in the 2-day matrix? So there would be at most n square
N
number of
square.
times.
Yes.
And say, and then to convert those n square values into this form would again be requiring say effort of the order of yes, because I can make a bitwise shift kind of the thing to say to get the value of 2 raised to
Yeah.
the power n of n. Yeah.
Right. So
Yes,
every
yes.
individual computation would take you order n, and there are n square computations you need to do. So order n cube.
Yes, yes, yes.
Yeah. And again, to compute the determinant, you would require order n cube. So the running time is still order n cube.
Yes.
Yeah. So now again, there are two cases. Case one is no perfect matching. Case two is G has a perfect matching. So what happens when there is no perfect matching?
So when there is no perfect matching, then the value of the determinant would be equals to 0.
Yes, because why the determinant? Okay, so even over here, we are still evaluating the determinant of the two-tailed matrix at some point, right? The point is no longer random; it's two to a random value, but still a point, right?
Yes, yes.
So if the two-tailed matrix itself has zero determinant, and any evaluation of it must also be zero, right?
Yes, yes.
Yeah. So matrix evaluated at the point 2 to the WE, where E is in E. So this is also zero. Yeah, so in this case, the algorithm always succeeds. Again, the interesting case is when she has a perfect G. Okay, let me add a page over here. And the, okay, so I want to claim the fault. What's the claim number? Oh, here it's just the first one. I was using 2n, so 1/2. Yeah, so now we'll prove the following that the determinant of m is not equals to 0 with probability at least half. Okay.
Yes.
Yeah. So now what's the determinant of m? Yeah, okay. So, yeah, so this is what the determinant of m looks like. And all I've done is substitute the values over here. Now we know that when G has a perfect matching, there exists a permutation that this thing is non-zero, right?
Yes.
So there exists a permutation that the coefficient of this summand is non-zero. So
And so
this
what's
sum
this?
is not empty.
Yes. So what this coefficient here is? I mean, what does it
So
imply?
it would be either -1 or +1, right? Because it's -1 to the sine of sigma.
Mm-hmm.
Yeah, so this is +1 or -1. The exact coefficient doesn't matter. What matters is that it's non-zero. So this sum is not empty.
Yes.
Okay, so yeah, this is not entirely accurate. I should at least write something over here. Okay, this is no longer in SN. Okay, let me erase this and let me write it like this. Yeah. So all I've done is replace mi sigma I by its values. Now, if okay, so if mi sigma I is non-zero, then the value would be 2 to the wi sigma I. Otherwise, this would be 0, right? So removing all the zero terms, all I would get is sum over sigma in perfect in the set of perfect matchings, product I in n to the wi sigma I, right?
That's true, but yeah, so it's true, but so when I take the product of so many exponential terms,
Mhm.
I mean, what would happen?
Oh, so not,
So effectively, I would be adding all these things, like say,
yeah. So it won't be too large. The value won't be too large. So W, yeah. So you get this, right?
yes, yes, yes.
Okay. So now I want to use the isolation lemma. And isolation lemma apply. Okay, what does it apply to? It applies to the weight functions of the system and say what the weight function is, right?
I could not hear you, but I could understand that this lemma applies to the weight functions, and so weight function applied to the subsets. Yes.
Right. So I need to come up with a universe, and in that, and for that universe, I need to come up with a set of families, and then I can apply the isolation lemma to that set of families, right? Sorry, to that family. F.
Okay. Okay.
Yeah. Okay. So let Q. Okay, I want my elements of the family to be perfect matchings. So let okay, I would need more than 2n. I would need 2n square over here. Yeah. So let U be. Actually, no, I can get away with something less. Yeah, let me do it like this. Okay, yeah. So let the universe just be the set of edges. So this looks like I comma j, right?
Yes.
And cryptech be this set of all perfect matches. So every element of cryptech is going to be a subset of U, right? Because every matching is just a subset of edges.
Yes. Yes.
Yeah. So I have a universal set. I have a family, and yeah. So now, oh, by the way, this okay. So then I can write this as follows. Yeah, because okay, this is slight abuse of notation, but we know that okay, every permutation like corresponds to a perfect matching, right?
Yes.
Yeah, so I can write it like this. Now, look at this expression. What is it? So, if sigma were f, this is just the sum of the weights of the elements of sigma, right?
Yes.
So, I can write it as yeah, I can write it like
So
this is
I
fine.
cannot. Yeah. Uh, so yeah. So weight of sigma. Why so? I mean, so weight function, weight of S used to be what? So weight of S used to be
The
the
sum
weight.
of all elements in S, right?
Yes. Yes.
Yeah, so even though sigma is a permutation, over here I'm treating it as a perfect matching, right?
Yes.
And okay, what does a perfect matching look like? It looks like 1 comma sigma 1, 2 comma sigma 2, 3 comma sigma 3, and so on. So the set
Yes.
it would be 1 comma sigma 1, n comma sigma n. And that's exactly what's over here, right? So you are summing up all the weights 1 comma sigma 1 to n comma sigma n, right?
Yes. Yes. Yes.
Yeah, so this is the weight function associated with sigma. So is this fine?
Yes. Yes. It is clear.
Okay. So now let us suppose that there was a unique sigma with the minimum weight. Okay.
Mhm.
Then what I can do is, okay, what do I want to prove? I want to prove that this is not equal to zero, right? With high probability.
Yes. Yes.
Yeah, and I would use the isolation lemma. But for now, let's forget about isolation lemma. Let's just assume that there exists a unique sigma such that this there exists a unique sigma for which the weight of sigma is minimum.
Unique
Okay,
sigma for which the weight of sigma is what?
minimum.
Okay. Yes. Yes. Yes.
Yeah. So exactly what the isolation lemma would give us.
Right. Right. So yeah, and
Yeah.
what is n? What is n here, and what is w then?
The unique sigma that this quantity is minimum 2 to the weight of sigma.
Hmm.
Okay, but okay, so let me write down it like this. Weight of sigma 1 plus 2 to the weight of sigma 2 minus 2 to the weight of sigma 3 and so on, right? So this entire sum looks like this, right?
Yes, but then why to use minus here and not plus?
Oh, because minus, so
Uh,
some of these powers of 2 would be plus and minus, right? Because of this thing.
oh yes, yes, yes. Yeah,
Yeah.
right.
That comes from the yeah. Okay. So this sum looks like this. Now suppose that one of the there was a unique minimum over here. So let's say 2 to the sigma 1, 2 to the weight of sigma 1 was minimum. Then I could have written this entire thing as 2 to the weight sigma 1 times 1 plus 2 to the, let's say, k1 minus 2 to the k2 and so on. Why? Because I am taking 2 to the weight of sigma 1 common, but because all of these are powers of 2 and 2 to the weight of sigma 1 is the smallest, it divides everything else, right?
Yes, yes.
Yeah. And what would k1 be? K1 would just be weight of sigma 2 minus weight of sigma 1.
Right.
Yeah. So now what happens is this entire thing, it is an even number, right? Because k1, k2, k3 all would be at least 1.
Right.
Yes, weight of sigma 1 was a unique thing which was minimum. If weight of sigma 1 and weight of sigma 2 were both minimum, then this need not be even because 2 to the k1 would be 2 to the 0, which is 1.
Yes.
But since that is a unique minimum, weight of W, weight of sigma 2 is at least one more than weight of sigma 1. Weight of sigma 3 is also at least one more than weight of sigma 1. And so all of these are at least one. And so this quantity looks like sum of powers of 2, each power greater than 1, right?
Yes.
So is this fine?
Yes, I can understand this. Yeah.
Yeah. So, okay, so now what do we have? We have 1 plus or minus an even number. But 1 plus or minus an even number can never be 0, right?
Yes. Some quantity would be there.
So this entire thing is nonsense.
Right.
The high level idea. All that is missing is, okay, how do you find weights? So is this fine?
I could not hear you. I mean, so the last
So
wording you
all I
said.
was saying is that all that now remains to do is to show that I can somehow find weights. Sorry, I can somehow find weights such that there is a unique minimum over here, right?
Yes.
And that I can do using the isolation lemma. So from the isolation lemma, this quantity is at least 1 minus size of, okay, size of U over here is size of E, right? But size
Yes.
of P can be at most N square. So this is at least half.
And by the cardinality of, the mod of W is equal to 2n square.
So I just because I want this to be 1 over 2. Because
Oh,
size of E can be at most N square.
yes.
Yeah. I mean, in fact, even if I had taken this to be 2 size of E, it would have worked.
Yes.
Because this would cancel out. But yeah, I'm just taking 2 N square for simplicity. Okay, so this happens. Now, if, okay, so there, then, uh, okay, let this unique sigma Yeah, so all I've done is taken 2 to the weight of sigma star common, which is equal to what we because 1 plus or minus an even number can never be 0, right?
Yes, yes.
Yeah. With probability at least half, the determinant would be non-zero, right? Hmm. So is this fine?
Yes, this is fine. Though, even though this is slightly difficult to understand uh, for the first time, but but I could
Yeah.
understand the cuts of.
Okay. Okay. So okay. So I said that we would. Okay. So the reason we are doing 2 to the WE is from the determinant would have some nice. Its value would have some nice structure, and we would use this, right? That's what I said at the beginning.
Yes, yes, yes.
Yeah. So, okay, I wanted to show that structure now, but it's more relevant to the search version of the problem. So I'll prove the exact, okay, I'll write down the exact claim and the proof next time. But let me just quickly show you that. Okay. So, yeah. So if the determinant is non-zero, then with probability at least half, it looks like this, right? Unique thing over here, and all of these are at least powers of 2, which are at least 1, right?
Yes.
Okay. So now my question is, what is the largest power of 2 dividing this quantity?
Okay. So the largest power of two that will divide this thing is okay. So some even power. So say if the value of some even number is say two, so
It's
then this
exactly this, right?
yeah. So this is yeah
Why?
two raised to
Because
the power of
this
two.
is 1 plus or minus an even number. So this
Yeah.
number is going to be odd. So
Yes.
determinant of n looks like 2 to the weight of sigma star times an odd number. But from here, you can never get a power of 2, right?
Yes.
So the largest power is weight of sigma star, i.e. the weight of the unique minimum weight perfect matching, right?
Yes.
Yeah, so, and we would use this fact that the weight, the largest power of 2 is the weight of the is 2 to the weight of the unique minimum perfect matching to find this perfect matching. Yeah,
Can you repeat this last statement? The
yeah.
statement that you
So
made
I
that.
said that I said that we would use the fact is 2 to the weight of the unique minimum perfect matching to matching in parallel.
Mhm.
Yeah, so this is what we'll do
Okay.
next time, and this is the reason
Yes.
setting xe to be 2 to the we instead of we and then find the determinant.
Mhm. Mhm.
Yeah. So
And
is this
are
fine?
there some,
Yeah.
yeah, yes, are there some simple use cases of the isolation lemma? It is true that the isolation lemma has been used here, but there must have been some simple use cases also. Just to understand the lemma.
So I don't think there are, I don't know of many other simple cases. So over here, what's happening is look at this set script f, right? It's the set
Yeah.
of all perfect matchings in G, but this set can be very large. It can even have, in fact, it can have exponentially many elements, right?
Yes, yes, yes.
Yeah, so isolation lemma is helpful because in the in the statement of the lemma, the size of f, which can be exponential, does not appear anywhere, right?
Yes, yes.
So if I have a guarantee that the size of f is polynomial, I don't even need the isolation lemma. I can just use the Schwarzschild lemma.
Mhm.
Yeah, so because of that reason, there haven't been too many other simple applications of like isolation lemma. Because for something simple, you can just use the Schwarzschild lemma.
Okay.
Yeah, and as we saw, like even over here, using the Schwarzschild lemma gave us a much simpler algorithm, right?
Mhm.
Because over there, I
Yes.
only had to worry about a polynomial. Over here, I had to worry about a universe and a set of families of the universe, and somehow ensure that my random choices give me the weight function, right?
Yes. But then the sign
Yeah.
of the inequality is different in both the lemmas, in the isolation lemma and then the previous one. There it used to be less than or equals to the d divided by the mod
Okay,
of
so
a.
even over there, I could have written it like this. Uh, Probability that f of a is not equals to 0 is at least 1 minus d over size of s.
Oh, I see. Yes, yes.
Over here, this is the more natural statement. Over here, natural statement.
Yes, yes, I understood. Yeah.
Yeah. Okay, so do you have any other questions?
No, no, no question. Yeah.
Okay.
Thank you so very much.
So
Thanks,
then,
Siddharth.
yeah, I'll upload the notes as well as lectures today, and then we can meet next time.
Sure. Thank you so much.
Yeah.
Bye
Yeah.
bye. Good
Thanks.
night.
Bye. Recording.